So good morning, everyone, and welcome to our 6th monthly Ocean Plastic webinar. This morning, we have two speakers, Tim van Emmerik and Alexandra Ershova. Tim is an assistant professor at the Hydrologic Sensing in Wageningen University. Sorry for not saying this the correct way. He currently works on the development of methods for riverine plastic pollution monitoring using, for example, citizen science, drones, and spaceborne remote sensing. Current research projects focus on rivers in the Netherlands, such as the Rhine and Meuse, in Vietnam, the Mekong and Red rivers, and Indonesia across Java. Before joining the Wageningen University, he worked at the Ocean Cleanup and Delft University of Technology. And then we will have Alexandra Ershova. She is an assistant professor at the Russian State Hydrometeorological University. She's also head of the Laboratory for Plastic Pollution Research, called Plastic Lab, in St. Petersburg in Russia. She focuses on marine litter beach monitoring in the Gulf of Finland, which is in fact a huge estuary. They test different methods for microliter sampling and on sandy beaches. They also try to develop a universal methods working on both marine and river beaches. Their lab also carry out research in the Russian Arctic, where they test and develop methods for water sampling in high biological productivity conditions. So first, Tim, and then followed by Alexandra, will present their work on beach and riverine marine plastic monitoring, and we'll answer your questions afterwards. So if you want to ask questions, please go on your web browser to sli.do, and then enter the key OPW, and you will be able to ask all your questions there. You can also vote for questions, and we will ask them at the end of their presentations. So first of all, Tim, if you want to share your screen, and I will leave you to it. And all right. Yeah, works well, and the floor is yours. Thanks.
Okay, let me quickly resettle this a little bit. Yeah, good morning and good day, everyone. Thank you very much for having me today. Thank you, Audrey, for the nice introduction. And yeah, as nicely put, I will talk today about the riverine microplastics and how to find them. I'm an assistant professor in hydrologic sensing at Wageningen University. I know it's the most Dutch name you can think of, but with a little bit of practice, it's not so difficult to pronounce. And me and my team are working on developing methods to measure microplastics in rivers and river systems. And that's what I want to talk to you about today. Now, to illustrate why this is so important, I'll start with a slide from a paper that was published, I think, last week or 2 weeks ago by Stephanie Boyal et al., where they made a new estimate of how much plastics are entering aquatic ecosystems, so river, lakes, and oceans on an annual basis. And yeah, to cut things short, it's a lot. There is millions and millions of tons of plastics being emitted from land into aquatic ecosystem. Now, on a global level, this is already quite worrisome, but if we zoom in, it's actually even more of a problem because we have no idea where these plastics are really emitted into aquatic ecosystems. We don't really know when they're being emitted, and we also don't really know what kind of plastics are really emitted. So that emphasizes the need for data in the field on local, regional, and global scales. And that's basically the issue where me and my team are trying to work on. So what I want you to remember from today is that microplastics have a very clear impact, but we're only at the start of measuring and understanding the abundance and pathways of microplastics into the environment, and a lot of more research is needed. There is a big need for new and harmonized monitoring methods to make sure that we measure consistently over time and space. And I would like to encourage you all to explore new methods to measure plastic yourself and to iterate in order to arrive at consistent measurement methods and better data in order to solve this global plastic issue. To make sure that we're all on the same page, yeah, what are we actually talking about when we talk about plastic, or when I talk about plastics? We all know that plastics unfortunately come in all kinds of sizes and polymer types and shapes and what have you. For me, the most important thing is looking at the size ranges. So I guess you're all familiar with the nanoplastics, the microplastics, maybe the mesoplastics, and then the macroplastics. I don't focus on all of these types of plastics. I really focus on the large stuff. So everything larger than half a centimeter, mesoplastics, macroplastics. That's what we're really looking at. And luckily, my colleagues here at Wageningen University, they focus on the micro and the nanoplastics in rivers and oceans. So that's really quite complementary. Why I focus on macroplastics, I want to illustrate with this slide here, because luckily there's a lot of research going on, and there's a lot of research already done on the abundance and the types of plastics in all aquatic ecosystems. However, if you look at where all this research focus on, there tends to be a very strong bias towards marine plastics for a good reason. But if you look at all the research done to date, the vast majority is really focused on marine ecosystems. Now, if we then take a look at the plastic research that is done on rivers, you also see that there's a bias in riverine plastic research with a very strong bias towards microplastics. So even a shorter or a smaller fraction of the total amount of research on plastics is focused on river macroplastics. Now, if you zoom in even further, we unfortunately also see that there is a strong bias in the studies on riverine macroplastics, because they tend to be biased towards European and North American rivers and river systems. Unfortunately, it's safe to assume that the most polluted rivers are actually distributed over the whole globe, and that emphasizes again that there is a strong need for global measurements and data on riverine macroplastics. Because it's quite clear that they have a negative impact. Let's not talk too much about the effects and potential effects of microplastics. There is evidence that it's very harmful, but for microplastics, the large plastics, it is so extremely clear what the negative impacts on aquatic life and human livelihoods are, in fact. It is the macroplastics that cause animals to die or to get injured, whatever you find, unfortunately. But they also have a very clear effect on our lives. So they cause a lot of damage to fishing vessels or aquaculture. They cause blockage of urban waterways, further increasing flood risk in urban areas. And macroplastics are the main source, or assumed to be the main source, of marine plastics, and assumed to be the main source of microplastics in river systems and beyond. So understanding macroplastics, the sources, the sinks, the transport routes is really crucial if you want to solve the global plastic challenges. And that is also where we focus on here at Wageningen University. Now, the big issue with macroplastic in rivers is that there's so little consistent data to date. So we are not the first ones to measure plastics, but all the research out there is unfortunately rather inconsistent in time and space. There is a lack of data, so it's also very difficult to increase our fundamental understanding of plastic transport from source to sink. So the main question that I work on is, how do we measure plastics? How do we measure macroplastics consistently over time and space? And using those data, using those observations, how can we determine the sources, the sinks, and the transport pathways of these plastics from source to sink? I have a background in hydrology. I'm a trained hydrologist at Delft University of Technology, so I specifically try to look at the relation between hydrology and plastic transport through rivers and exploring the role of rivers. Unfortunately, plastics are found in every compartment of the river system. So really from plastics on riverbanks to plastics deposited on the riverbanks or in the floodplains and repairing vegetation. Of course, the floating plastic debris suspended in the water column, plastic in the sediments, and plastic that is temporarily ingested by biota. And see that to date there's quite a bias towards developing methods on that focus on the floating plastics and plastics on the riverbanks. So yeah, if there's no methods for the other compartments, how do we ever arrive at a sort of holistic understanding of plastics in river systems? Now, I said I'm not the first one to measure plastic, luckily, and there's been a lot of pioneering work done in the last 10 years. But if you sort of compare and or summarize what has been done to date, you see that the methods that are being applied, they vary quite a bit. So in short, we can sort of distinguish four classes of measurement types, ranging from active sampling, where you go out with your net, either a handheld net or a net that you deploy from a ship or from with a crane from a bridge, where you actively sample debris that you can analyze. We also have what we call passive sampling, where you use debris that is already accumulating somewhere naturally, so either in cleanup devices or in, for example, on riverbanks. There is the so-called tracking experiments, where you release either GPS trackers or labeled trackers that you can follow through river systems. And finally, there's my personal favorite, the visual observations, where you either, for example, stand on bridges and count the items that you see floating by, or you use OSPAR-like methods where you count all the plastic items on a transect on the riverbanks. Despite its simplicity, it really gives a fast order of magnitude estimate of how much plastics are abundant in the system. Now, if you look at reality, it's a little bit of a mess, literally, because to date, everyone is trying out new methods, trying to use different methods for measuring the same kind of plastics, then also reporting their results on different units. And that makes it very difficult for us and for others to sort of to get the big picture and to compare the results of measurements between rivers over time and over space. So what we propose, or what we proposed, is to just start simple. If you're interested in river plastic monitoring, and I hope that all of you will be, and that everyone will be at some point, just start simple. Start with the simple measurements that are low cost, cost efficient, and that give very rapid information about the state of plastic in your river system. So start with simple visual observations. Count items floating in your river from bridges, count items on the riverbanks, and it gives you a very quick insight in how the item flux and the item stock in your river system. If you have more time and resources available, you can focus on getting samples through either active or passive sampling to build your plastic statistics. So, for example, what is the average mass per plastic item in your system? Because if you have that, you can convert your item flux or your item stock into mass flux or mass stock in terms of plastic mass. If you have even more data or time and resources available, you can also explore relations with hydrology and meteorology or other factors that are important. Because if you have those, if you find these empirical relations, you can extrapolate your plastic observations over time and space to make a more accurate forecast of seasonality of plastics, but also to identify potential hotspots of plastics along river systems. In the remainder of today, I would like to just give some examples of some recent work that we've done with basically following this philosophy. So you can, for example, apply this to a single cross-section in a river. If you're really interested in, hey, what's going on in a specific location in a river system, you can just go there and measure. It's not that difficult, and what you get is a very nice insight in how plastic is distributed over the river width and how it varies with the season. That's what you see here on the right. And the interesting and sad thing is, or challenging thing, is that plastic transport can easily vary with a factor of 10 throughout the year. So that also emphasizes the importance for more long-term measurements, because if you only go there once, you still have no idea how this sort of evolves over time. You can also do these kinds of measurements along a river to identify hotspots or look at how where the plastics may go or where they're introduced in the system. This is an example of some measurements we did in the River Seine in France, where we measured plastics at 3 locations along the river from upstream of Paris, downstream of Paris, to a location closest to the river mouth. And what you see is that if you just go there for during 2 seasons, you again see that there's quite a big difference in the spatial pattern of the amount of plastics in such rivers. So that really gives some insights in not only the response to hydrological regime, but also to potential sources and sinks of plastics. A very recent study that is now in press in environmental research letters looked at the abundance of plastics on riverbanks in the Dutch Rhine-Meuse Delta. And this study really emphasizes how much insight you can gain from long-term monitoring. So even though long-term is still relative, we could use 2 years of data collected at more than 200 locations along the Rhine and Meuse rivers in the Netherlands. And that gave a lot of new insights in sources. So we saw that there were hotspots around specific cities, unfortunately also at the borders with Germany and Belgium, and all the way downstream into one of the national parks here that is located in a tidal zone. And probably because of the bidirectional flow, a lot of plastics are deposited there in the riparian vegetation and the floodplains. But besides these dynamics, it also gives a lot of insight in what kind of plastics you actually find in these river systems. And when we looked at the top 20 most abundant items, using more than 150,000 analyzed items, we found that the most abundant items in the Dutch rivers were fragments. And that's good to know, because that tells us a couple of things. It tells us that these plastics are probably in the environment for quite some time already. They had the time to fragment into relatively small pieces, so small that they're not easily identifiable as specific items. And then there is, in turn, also says something about the efficacy of item bans, for example, because I mean, it's a good thing that we're rethinking what kind of items and plastic items we're using, but it's not a silver bullet. It's not a silver bullet to just ban plastic straws or bags, because these are actually not the most abundant items that we find in river systems. Now, similar methods we can also apply to look at hotspots in urban areas. So on the left you see the first plastic hotspot map of an urban water system. This is actually the city of Leiden. And again, with these simple measurements, you very rapidly identify where you find hotspots in urban areas. And in this case, it's quite interesting that well, in the city of Leiden, students not only cause hotspots of coronavirus, but they also obviously cause or are associated with hotspots of plastic pollution in the city. Similarly, you can also do this for larger urban areas, such as the city of Jakarta, where with a combination of strategic measurement locations in the urban water system and a simple hydrodynamic flow model, we were able to, for the first time, provide a accurate estimate of the yearly emissions of plastics from the Jakarta rivers into the ocean. We estimate that it's about 2 million kilograms of plastics that are emitted into the ocean every year. Now note that this is a lot, and this is really worrisome. We also think that this is only 3% of the total amount of plastics that are leaked into the environment per year. So that shows that the vast majority, in this case 97% of the plastics, they remain somewhere on land and somewhere in the river system, maybe in the river mouths, maybe somewhere else. So the fraction that actually leaks into the ocean, that is emitted into the ocean, is just a very small part of the total amount of plastic pollution in terrestrial and aquatic ecosystems. So with these simple measurements, we can also finally do a global comparison. So this is a paper that came out at the end of last year, 2019, where for the first time we could compare over 20 river systems in Europe and Asia. And that's quite important, because with these simple measurements, you can really rapidly assess whether the river that you're interested in, or the river where you live or work on, whether that is located on, let's say, the cleaner side or the more polluted side of the spectrum, because that in turn determines what kind of long-term strategies and methods are most appropriate for monitoring plastic pollution in that river system. Now, people often ask me, okay, all this visual observations, sure, it's fast, it's cost effective, and it gives a lot of insights. But can't you do it in a smarter way? Short answer is yes, we can. And that's exactly what we're exploring. So recently, we developed a citizen science app in collaboration with the University of Zurich that allows everyone, so hopefully also you, to collect data on river plastics that are floating or located on riverbanks. So the app is called Crowdwater. It's a hydrological app with a module now to measure plastic pollution. And the cool thing is that there's so much data coming in right now, also from places where you don't expect it. So this is an example from Norway, plastic pollution measured in the August Elva. And this is a location where normally you would not get funding to set up a long-term monitoring campaign, because these rivers are assumed to be clean because they're in Norway. Well, we actually demonstrated with some simple measurements that they're actually not so clean, and that there's also some serious things to be done here to reduce plastic pollution. So I hope to encourage you all to download this app, Crowdwater, and start collecting data on plastics in rivers all around the world. At the same time, we're also exploring other high-tech solutions, such as the use of drones, which is working pretty cool, especially if there's no bridges or other infrastructure available. We're looking at the use of cameras, both RGB and multispectral, and we're also working now on using remote sensing imagery to detect and track plastics in river systems. And although I'll leave it at that, the first results are pretty promising. So I hope that there will be more to share soon. And to end, I would like to just emphasize or address a couple of challenges that we currently work on, and that might provide some outlook to future research for us, but also for you if you're interested. I think one of the main challenges here, and that's maybe also one of the questions you have, is, hey, we're focusing a lot on the surface right now, so what about all the plastics that are below the surface? It is often assumed that plastics are maybe at the top of the surface, or that the floating fraction is the majority of the plastics. Unfortunately, some preliminary results show that this might not be the case at all. So some preliminary results from data collected in Spain actually showed that about 80% of the plastics could be transported below the surface, and that's quite worrisome, because these are the plastics that are not monitored in current monitoring strategies, but these are also not the plastics that are focused on in most of the cleanup technologies that are being deployed around the world right now. So we might be missing the most of the plastics by focusing on the surface. At the same time, we're not really sure about transport mechanisms yet. We often assume that surface runoff and wind and rain and river discharge, that they cause plastics to be transported from source to sink. But we actually have no idea how plastics end up in rivers and how they're transported into the ocean. And although linking this to hydrometeorological variables makes sense, we really need fundamental experiments to demonstrate that this is actually the case. And then finally, I'd like to close with I think two very important open questions and challenges, of which the first one is the question what the role is of estuaries. We know that rivers are connected to the oceans through estuaries, and the tricky thing about estuaries is that they have bidirectional flow. So there's a tidal cycle, and the river or the water in the estuary basically flows in two directions during the day. And we think that it actually leads to estuaries and river mouths acting as a temporary sink of plastic pollution, because it's just moving back and forth, and it's just sitting there waiting to be flushed out when there's maybe a peak flood event or some other extreme event. So not only causing a lot of additional local harm, but also functioning as a sort of point source in time and space in response to a hydrological event. That's exactly also the final challenge that I want to share with you, and that is the influence of floods. So far, most assessments, they focus on, let's say, normal conditions, but there is some evidence that supports that it's actually the floods, it's the extreme events, could be both in terms of wind, but also in terms of hydrology. It's these flood events or extreme events that may cause the most mobilization of plastics from source into the aquatic environment, and in turn to the ocean. Oh yeah, so it's a good day today because actually today our paper came out on exploring the role of estuaries in plastic transport from river into the ocean. So yeah, if you're interested in this, go to Frontiers in Marine Science and you find our new paper, which is really short, so it's there's no reason to not read it, and it's open access, of course. So to summarize, what I want you again to remember from today is that microplastics have a clear impact, but still a lot of research is needed to more accurately measure microplastics and study the sources, sinks, and pathways. And we need that to effectively reduce, prevent, and clean up microplastics from terrestrial and aquatic ecosystems. And hope that together with me, you'll never stop exploring, measuring, and iterating on measuring plastics and trying to reduce plastic pollution in the environment. Yeah, so to finish off, just an overview of all the people that contribute to all the cool research that we're doing. I'm definitely not doing this alone. And also for you, if you're interested in this kind of work, if you want to do your thesis or are looking for other kinds of collaborations, please feel free to get in touch. And I think with that, I'll give the floor back to Audrey.
All right, thank you, Tim, for a very interesting presentation. We will switch to Alexandra now. I think you gave her a really good introduction by saying that the estuaries are a really important place to dig in. So I would invite Alexandra to turn on her camera and turn on her mic so we can...
Again.
All right, hi again. So if our viewers have questions for Tim and later on to Alexandra, please log on to slide.do, hashtag OPW, and you can ask your question there and we'll read them to Tim and Alexandra at the end. So here we are set up. And yeah, Alexandra, the floor is yours.
Okay, thank you. Thank you, Audrey. Yes, I think that Tim had also very good introduction to my presentation as well, because we have much in common. Our place of interest, our place of research, I mean, location, it's St. Petersburg and the Gulf of Finland, of the Baltic Sea. Much in common with the Netherlands, by the way, because we have the same problems with storm surges, with flooding of the areas and the influence of the rivers at the same time. So I come from St. Petersburg, and as I said, this is the part of the we are like located on the very tip, eastern tip of the Baltic Sea, and it's far most eastern most part in the Gulf of Finland. And why? First of all, just a few points about this area, the Baltic Sea in general, and why so much research is focused on this sea. In general, this is a unique sea, unique ecosystem because of its high sensitivity to the anthropogenic load. It has many problems, and to solve these problems, we have the HELCOM Baltic Sea Action Plan, which is the regional strategy for a healthy Baltic Sea. It has a lot of points and a lot of targets that need to be reached by 2025, etc. But now we have the new Marine Litter Action Plan. It's a different document that also focuses on the new problem, the marine litter, and there is this the main thing is to develop the relevant indicators and relevant target values for this area, for this region, for entire region that is bordered by 11 countries, coastal countries, including Russia. Russia being not the EU, so we are not the European Union, and we have totally different monitoring strategies, regulations, environmental regulation, etc. So this is quite a challenging task to develop these indicators in terms of marine litter. And now this plan focuses just like it's the first focus of this plan is now just to, in general, to manage wastes in this region. So the most part of this plan is devoted to the waste management practices. However, to get some overview of the marine litter pollution in general, we need some harmonized data based on monitoring strategies. That's why something that we have never done before in the Russian Federation and in this region, in the Gulf of Finland region. That's why, I mean, for Russia, that's why we are, for last several years, we are focusing on testing different methods, testing different approaches to monitoring to find out which one is working better and to get the overview of marine litter pollution in our area. So we're working in the framework of this joint project. We have many colleagues working on this project. This is actually the Gulf of Finland and St. Petersburg, where I live. Our study, we have many tasks in the frames of our research, actually, and not all of them are reached yet, achieved yet, as I would say. We are focusing mostly on macroliter and meso and microliter, but as we call it, large microliter. So the main point is to first to assess the litter which is visually detected, so does not doesn't need some very laborious techniques to identify the litter. So we are testing different methods, and first we needed to find suitable beaches for monitoring, because it's not an easy task for this highly eutrophied area, and that's why we have a lot of vegetation and algal mats, etc. So that was many tasks in this research, and those methods that are now developed for the Atlantic region, North Atlantic, which we are actually part of, yes. They are focused on macroliter and rural beaches and with no cleans, and it's ocean beaches. That's why our colleagues from the German Institute for Baltic Sea Research, they developed these methods for the beach litter monitoring for the Baltic Sea beaches, and they developed, and there are two of them. They are complementing each other because of the one method is focused on the wave rake line, the another one on the entire beach length, but they both are based on sieving sand, sieving and seeing, collecting the fractions that are visually detected by eye. I think you can ask more about these methods and how they were developed and how successful will they work for all other Baltic beaches. You can ask the authors. So I would or maybe I should invite them for this next talk about this Baltic Sea beaches in general, about these methods. But I want just to show you how this how it works for the estuary, for the Neva Bay, and for our quite complex conditions, because we have winters, we have ice in winter, etc., etc. Just in general, the overview of our area of research. It's Neva Bay. It's closed by the dam, same as in Netherlands. We have storm surges coming from the Baltic, and we need to protect the city with the dam that was built like about 20 years ago. So we have this kind of estuary that really serves as a sink for many pollutants. And as we will see next, that microplastics is not an exclusion. It's also sinks here. Also, it's a brackish water area, so it's not the real marine area. It's brackish. The salinity is very low because we have the Neva River mouth here. It's the largest river in Europe with a very high discharge. And also, together with that, we have the largest city of St. Petersburg. So a lot of wastes generated in the area. and some of it, of course, eventually comes into water, sinks here, stays in this area. This is just the pictures of them. Of the beaches, the typical beaches, long, sandy, and types of litter that we collect during our monitoring campaigns that we carry out through last actually 3 years now. Examples of the litter that we find. These are a lot of pellets, same as everywhere in the world. Pellets are actually the litter that is found everywhere on the beaches. A lot of glass and a lot of metal. And just some results that I want just to draw your attentions to that. As we expected from the very beginning, that we actually were expecting something. That's how it will work, because plastics, we were trying to find where it comes from, and it's kind of was obvious that it comes from the city, from the river, but it stays in the bay. So as you see, the blue is plastics. It doesn't really go through the dam, and it doesn't go through to the Gulf of Finland and then to the sea itself. So most of it comes from the river and stays somewhere here, sinks, not sinks, but stays on the beaches. The rest is more like metal and glass, and they have another origin. We think that they come mostly from touristic activity, or from some traffic shipping activities. And also another thing that we are kind of struggling with, because we have very different combination of plastic, metal, and glass, and all the methods, most of the methods are focused on measuring items per some square meter, or per kilometer, or per so in items. But if we measure weight of this litter, it's a totally different story. We see that the same beaches, these are just the names of the beaches, they demonstrate the largest pollution by items, like for example these beaches. And regarding the weight, because this is mostly plastics, as you see, we see that these beaches, they are not. They're here. I'm sorry. They are not the most polluted. Most polluted are with the heavier items are found on other beaches. And if you see that the number of items, they are very few, but they are much heavier because they are mostly metal and glass. So when we talk about methods, it's very important to combine these two measures. Otherwise, we can be confused by the results. And also, I would like to just demonstrate the work of our colleagues, because our team is quite big. We work on the Gulf of Finland area for quite a long time. We're on these ecosystem changes. We have the hydrodynamic model of the Gulf of Finland. It's based on the Princeton ocean model, and our colleagues tried to carry out first numeric modeling experiments with this model, and to model the particle distribution, plastic particle distribution coming from the river mouth. And actually, more or less, they were corresponding to our monitoring results. So we also see that because the bay is very shallow, and then it goes deeper and deeper, and this flood protection barrier is really closing the mouth and Neva Bay again with its fresh waters. So the plastic is distributed to the beaches, and more heavier items like glass and metal and other stuff, more heavier, they just sink. Most of it sinks right here and never goes through the dam. So this is kind of the pattern that is likely to be demonstrated in most of the estuaries, other estuaries, because of the fresh water mixing with the, and because of its because it's closed. I mean, our river mouth estuary is closed from the open sea, I would say. So these are like one of the general kind of challenges that we are studying, and in general about the pollution, the Baltic Sea beaches. We can say after these several years of research together with our colleagues, we can say that the Baltic Sea beaches, the pollution is much lower than in the other areas, like for example, the North Atlantic. However, our area, the Gulf of Finland and the Neva Bay, the Neva estuary, we have here in the easternmost part of it the maximum concentration of microliter, and it's really these concentrations are much higher than in any other areas of the Baltic Sea. So of course, this enclosed lagoon type, we call it lagoon type bay, it serves as an accommodation zone for some types of litter. And plastic is generally dominating, but we have a totally different picture in the northern and in the south coast of the Neva Bay. They differ dramatically due to hydrodynamics of this area, and we have more plastic on the north and much less plastic in the south, almost no plastic in the south. Also, we have this litter accumulation is mostly dedicated to wreck line zones, so the wave is breaking, so it doesn't really go further to the beach. However, this pattern is totally different after winters. So in spring, when we tried our monitoring in spring, we see that this line of the snow line, the ice line, it corresponds to the line of accumulation of litter. So the very important factor for freezing seas, for freezing water bodies in general, is of litter accumulation is the impact of ice, because ice is kind of transferring it further to the beach. What else? I think I'm also almost finished. To let you ask questions, and also, of course, storm surge events are a very important factor. Seasonal monitoring is needed for that, and to winter to take into account the winter factors and other things. And yes, maximum concentration is observed after winter. Regarding these methods, in general, we really like them, how they worked, because they are robust and cost-effective in general. They allow many things to see with bare eye, and do not need really laborious work with the instruments. However, whatever method we used, at least in this type of areas, estuaries, we need to take into account units of measure, because we need to combine both of the weight and items, etc. We need to take into account seasons, so monitoring must be focused on different seasons, especially if there is winter season freezing waters. And beach cleaning is also an important factor that we also noticed, because, for example, in the very beginning, in the first year of our monitoring, we had very clean beaches in the area of St. Petersburg, because we have this football championship that before which everything was like swept with all the beaches were swept, but after that we had the regular picture. Like last year and this year we had the regular picture. These beaches were much more polluted because there was not much. They were much less cleaned by the municipal services. I think this is it for me. Thank you.
Thank you very much, Alexandra. Maybe Tim can turn his camera and mic on again. So we can.
Still live.
All right, great. I will. Okay, so I changed into the speaker view so we can have the three of us together. So now I will go through the questions. We have quite some questions, and I think they're really interesting. But first, thank you to both of you, sorry, for your really interesting talks. All right, so one first question is, what is the best way to stop plastic releasing from river mouth into the ocean based on your studies? Do you think traps at the river mouth would work? Maybe Tim, you can start, and then Alexandra, you can follow up.
Well, this is a very good question, of course. First of all, like with many things, there's no silver bullet here. So there's no best way. Preventing plastics from reaching the ocean through rivers is really a combination of all kinds of measures. But in the end, preventing plastics to end up in the river in the first place is so important because, you know, once it's out there, it just gets so much more difficult to take it out. So yeah, just make sure, just try to do everything that you can to not have your plastics end up in the river system in the first place.
Well, I can add that it's the river traps. They are really, I think it's a good thing that works on small rivers, but like Neva River, like we have, it's a huge river. So, and like many other like Asian rivers, I think that no traps will work for. I mean, not they won't be so effective. You cannot really close the entire mouth to collect all the litter. So of course you can see the most management. The management should start from the waste management. So from preventing the waste to come to the water area.
Yeah, just to add to that, like, of course, I mean, it will be very difficult to sort of guarantee that no plastics will ever leak into into river systems again. And I think the way that we should look at it is a little bit similar to maybe oil spills, right? Like, we're doing everything we can to make sure oil spills don't happen. But if they happen, we know what to do in order to clean it as quickly as possible and most effectively as possible. And I think a similar mindset is what we need for plastics. So I think we should not try to, you know, to take it for granted that plastics are in rivers and try to find the best technological solution to continuously take out the waste, but make sure it doesn't end up there. Of course, we have to be prepared to take out rubbish when it's in there, and that I think can be a combination of litter traps or maybe more autonomous devices. And yeah, just to emphasize that Alexandra has a great point. I mean, if you're focusing on these urban rivers in Jakarta, it's a completely different story than these large rivers like the Mekong, like the Amazon, like the Rhine, because like the Elbe. I mean, these are rivers and they have river mouths that can be multiple kilometers in width, right? So it's you're never gonna find a way to close off that entire river cross section there.
Yeah, I totally agree, but I think that we're not going to solve the recycling and waste management problem in a couple of weeks. So probably working on all aspects is definitely something good, but for sure, focusing on waste management is number one. But we need technology to be able to clean the ocean and clean the rivers and so on. And from this, someone is asking about the Rake method that Alexandra shows. And the listener wants to know if you can keep a constant depth of sand while you're dragging the device.
Yeah, it's quite easy. It's because that's not a very, I mean, it's not very heavy to hold it, but it's heavy enough to rake it more or less constant depth. Yes. So because we work with this device developed by our German colleagues for several years, and then it's easy. Yes. So it's.
And it doesn't depend on the type of sand on the beach as well. Like if you have pebbles instead of like very.
That's the thing. That's the problem. We for all the sieving methods in general, yes, because most of the methods are there to collect more or less microparticles, they are focused on sieving sand. And for this, the sand must be as more or less small fractions. If it's coarse sand, like for example in the Neva River mouth, we had some difficulties with sieving this sand because it's larger than the marine sand. So yeah, that's why we are now working on how to adapt already these methods to our course sand. That's what I would say. Yeah.
Okay, all right. Do we know? Do we have any indication how the different type of plastics is distributed among the water column, but also on the beach? Like, do we have like ideas on like the type, like the polymers, like how do they, distribute in the environment? Maybe Alexandra, you can start with this, and then Tim can follow on.
Well, at least for our beaches, what we already observed that the most of the microparticles, but what we call micro, the large microparticles, yes, like from 2 to 5 millimeters that we can see by the eye, they're mostly washed ashore, and we collect them in the wave wreck line. So they are not really transported further to the beach. So they're mostly here. And in general, I like to add to the previous comments that in general, why the attention must be paid to the river mouths and the rivers, because it's fresh water. We are now talking about the different environment. It's not the marine environment. So that's why the most of the litter coming to these fresh waters, it sinks much faster than it does in the marine environment. That's why here we have to act like more quickly, I would say, to collect it and to see it, to find it. Because of course, I think that if we go deep into the floor, to the bottom, we will see much more litter that we have in the marine environment.
All right, Tim, do you have any thoughts on this?
Yeah, so I always start most of the questions with the answer, it depends. It really depends where you are, what system you're observing. Luckily, we're getting more and more data to compare different river systems around the world. And if you just look at typical composition, typical item composition, typical polymer composition, it already varies so much. Just comparing Vietnam with Indonesia, with the Netherlands, you have completely different items, completely different polymers. That has to do, I mean, in the end, it's sort of a result of the combination of everything that precedes the moment where you find it, right? So it has to do with consumption patterns. It has to do with waste infrastructure. It has to do with hydrometeorological conditions in that system. Just as a comparison, in Indonesian rivers, we unfortunately find a lot of, let's say, typical household waste. So a lot of foils, wrappers, plastic bags, LDPE, HDPE, multi-layer kind of plastics. In Vietnam, for example, we find way more polystyrene, specifically expanded, or the foamy polystyrene. So that is already very, very different for a river that's just a couple of thousand kilometers away, which is a couple of thousand kilometers away. Also, if we look at plastic composition along a river, it varies a lot, which makes sense. So, for example, the few rivers that have been measured at multiple locations, from let's say upstream to the river mouth, you see that in the more upstream locations, it's more likely to find foils, plastic bags, wrappings, etc. But they also tend to accumulate on riverbanks and in riparian vegetation. So if you go close to the river mouth, it is more likely that you have a larger portion of hard fragments, harder plastics, robust plastics, and less of the foil bag type of plastics. So yeah, it really depends a lot.
Okay, so if I can, Alexandra, do you have any?
No, I just agree to this. Yeah.
I just want to jump on it, since you're talking about how these plastic foils and so on entangle in vegetation. You were saying earlier that plastic bags, for instance, are not the silver bullet. Banning them is not the silver bullet, but like you're talking, and Alexandra did mention it, but like you did not talk about weight, like you're talking about counts, and like how do you take into account the fact that a fragment that is 5 millimeters, or like, no, you're talking about larger, but like 5 centimeters compared to like one big plastic bag or one big water bottle, like how do you take this into account?
Yeah, so I call that, it's a very good question, a very valid question. We try to build the so-called plastic statistics, right? So that gives a lot of insights. However, you're completely right. We know that that foamy fragments have a completely different mass and mass distribution compared to PET bottles or plastic bags. So what we try to do is we try to build statistics. So we try to build mass statistics for each of these classes, item classes, but also polymer classes, that allows us to, depending on the information that is available, to convert these item counts into an accurate estimate of the mass flux, or the abundance in terms of mass, concentration in terms of mass in these systems. And we already see that this is very different again for different rivers. So in some rivers you find that the average mass per microplastic item is around 10 grams per item. In other systems we found average mass per plastic item of 1 to 2 grams per item. So it's really, it can already like change with an order of magnitude. So it is really important to get these statistics right, or at least get an idea of the distribution.
When you're actually studying the number, you also have the count. I mean, you always have the number in weight as well, in terms of grams for your studies.
That's what we aim for. I mean, okay. That's definitely, it's a super important step. And of course, if you have no resources, this is it may not be possible. But we do emphasize to if you have the opportunity, get these mass statistics, because they're extremely important. Also to connect what you measure in the field to, for example, the statistics we have on consumption, on production, on waste infrastructure, on recycling. Because for that, yeah, if you express everything in counts, you cannot add it up. So you have to make that conversion to mass at some point.
So how would you, like, so you were presenting that app. I'm sorry, I forgot the name of your app, but like Crowdwater, yes. So like you're showing Crowdwater and other like drones technique of looking at the plastic waste, right? Plastic litter. But like, how do you transform this information from like citizen and drone science observation, I would just say, into actual numbers that are, you know, worthwhile for like scientific publications?
Yeah. So that depends on the river system. So I mean, ideally, we would like to work towards a sort of overall database of sampled plastic waste in each river system, in each water system around the world, right? So, for example, what we do with a very specific case in the city of Leiden, where we use the Crowdwater app to make these hotspot maps, we combine that information with data collected by people, citizens, who go into the canals with canoes and clean up the plastics, because these cleaned up or these extracted plastics we can measure again to get the mass distribution, to get the size distribution, to get the polymer distribution, etc. So by sort of combining these different efforts, in this case through us, or this project can also be another type of infrastructure, of course, we can combine the information from these different strategies into getting accurate mass estimates. Same for, well, the example for the drone that was developed for the river Klang in Malaysia, and we did that. I mean, we did multiple measurements at the same time. So we were exploring with using this using the drone and developing a protocol for measurements with the drones on rivers. But at the same time, we were also doing net measurements where we collected samples from floating debris in that same river, and that in turn then also allows us to to convert the item counts based on the drone images into mass statistics and mass flux.
All right. Okay. Cool. So we have a question for Alexandra. A listener is asking, since most of the plastic accumulates in the area before the dam, is it easier to clean up?
Well, I think if we know that it definitely accumulates there, that of course it's easier, because it's easier to point out to the our administration of the city that we need to more focus that the cleanups must be more focused on the inner side of the Neva Bay than in the outer side, because all these beaches that we are investigating, they are all public, but the cleanings they're called regular, but they are carried out like in different seasons, in different, depending on many factors, I would say. So of course, with these studies, we can show that, okay, your cleaning efforts must be more focused on these beaches, particular beaches on the northern coast and on the inner side of the bay, than on the outer side. But if we talk about the sources, and this is another story, we need to estimate to find out what are the sources of this litter coming to these beaches, and then this will be another recommendation to other authorities, I would say.
All right. I have another, probably close to last question, since the time is almost up. We have Thierry asking if we have some Mantanet measurements of plastic in the Baltic Sea and the Gulf of Finland to estimate the pollution compared to the open sea. So yes.
So the question is, what is the method? I'm sorry, I didn't get it.
No, the question is basically like, do you have open ocean, or like open ocean within your Gulf, some like Manta trail over there, and to compare it, if you were saying that you have less pollution on the beach near St. Petersburg compared to northern Atlantic, the North Atlantic, is it the same within the ocean?
With the water. I think that so far we are focusing on the beaches, because we also like experimenting with water as well, but I can't really say now about the reliable. We don't have like reliable results yet for the water, because we just come to everything. So for now we are focusing on the beaches, and we can definitely say that the beaches are in the Baltic in general are less polluted, but in the Gulf of Finland they are much more polluted than in the other parts of the Baltic Sea. What's happening in water, it's another story. We have colleagues. We have there was this Marlene project, I think, that was carried out. There are some other research projects that are going on in the Baltic, like with our Finnish colleagues are working with manta trolls in the Gulf of Finland, but I cannot give you the numbers right now. I don't remember.
All right, I think that was all the questions we had for today, and I think the timing is perfect. Would you have some? I would love you to both have some concluding remark on your work, and how, just like a perspective, like how should we go in one sentence further? What you think is the most needed to be done now from where you stand? Maybe maybe Alexandra, you can start, and then Tim can conclude.
Okay, thank you. I think that the most important thing that about the marine litter monitoring in general, that we, as Tim mentioned, we have too many methods. We need to harmonize all the methods to get the comparable data. That's the most important thing that we need to do globally, to harmonize the methods and to have one unified method. But I don't think it's very easy to do. So it's not an easy task. So it will take some time.
Hopefully not too long, so we can go further on this. And Tim?
Yeah, I would just like to end with emphasizing the need for data. Only with data we can focus our efforts. We can make sure that we demonstrate the effect of measures, that we can express the level of pollution in rivers or in estuaries or the ocean. and that allows us to finally get a fundamental understanding of how plastics end up in the aquatic environment. And all of those steps are needed to solve this global challenge.
All right, so we need more data and harmonized data so we can all work together. I think that's a really good plan.
Yeah.
Hopefully we can do this in the future. Thank you very much to both of you for amazing talks and great answers to the questions from our listeners. And I hope I will meet you in real person someday. And we'll see you again soon on our webinars. Thank you very much.
Thank you very much for having us. It was really great.
Yeah,
Thank you. Bye-bye.
Bye-bye.